Hello everyone. So this is the fifth week of the interaction session on control system. We'll be dealing with many concepts and starting from robotics, it would be basics and selected advanced concepts, right? So yeah, just a brief introduction about me. My name is Soumya. I am a PhD student at IIT Gandhinagar. And so I'm your TA for this course and I am taking this course tutoring for it, and it has been 5 weeks. I think you are already clear with what you have learned. So we initially started with basic introduction to robotics, science and technology, right? It was like modeling and analysis of robots and main elements of a robot. We started with types and classifications and all of that. We moved forward, learned some linear algebra, learned some elements of robots, what are joints, links, DH parameters, etc., right? After that, we moved to kinematics of the robots. We saw it for serial robots and then for parallel manipulators. I think both of them are clear with you. So for serial robots, we have seen how do we do direct and inverse kinematics, and how inverse kinematics is a bit tougher when we talk about serial robots. But when we talk about parallel robots, it's not the same. It's kind of opposite. The direct kinematics of parallel robots is not that simple as that was for serial robots, but for inverse kinematics it is relatively simpler because we get an exact solution. And we have learned a couple of methods. We learned about how do we use Sylvester's method, how do we use elimination technique, and how do we solve it as an optimization problem, right? That all of these were covered. So last time when we talked about kinematics of parallel robots, we learned a number of things like how do we solve the direct kinematics, and what is the mobility of parallel manipulators, and what is the inverse kinematics of parallel manipulators. And at the end we saw that how do we write the direct kinematics of Stewart platform manipulators, right? That is the best example of parallel manipulator. Today we'll look more on the application side of parallel robots, and this is something that this in a way, so there are a couple of things in which this course is different from other robotics course taught. But uh, when we talk about the main difference that you'll observe is that in all the other courses parallel robots are not covered as such, but in this course we have application of parallel robots as well. And all of this work is the research work which is done under Professor Ashitava Ghoshal at ISC Bangalore. So from there, we have this research papers. If you want, you can look at them. I think you've gone through the lecture. And if you've gone through the lecture, you would be clear with what is being taught and how they have done the research, how they have done the simulations, and how they have deployed the hardware. You might have seen that there is sun tracking, trade-off, parallel manipulator, and then how it is being compared with the conventional sun tracking systems. So, just building upon that, we'll just have a brief recap of what is being taught, and after that, we'll move to some questions. The questions will not be very tough, it will be simpler questions and answers, but yeah, all of them would help you strengthen your concepts and solve your assignment, of course. Okay, so if I just start with what was taught in this lecture. So, the three important agendas that have been covered in this lecture are sun tracking using parallel manipulators, the second is Stewart platform, as a force torque sensor, right, and vibration isolation using Stewart platform. Right. So these are the things that have been basically covered, and this lecture basically connects robot kinematics, statics, singularities, and design optimization to real engineering systems, right? So The very first question that one can have from here, and I think you might have answer to this question already, but why do we need sun tracking? Why do we need to track the sun? So, all of you obviously know that sun does not remain fixed in the sky, right? It moves about 180 degrees in 12 hours, right? So, if we keep a mirror fixed, sunlight will miss the receiver, right? So, if sunlight is not falling directly on this mirror, and the angle of incidence is equal to angle of reflection, right? So you have a normal in between. So if the angle of this is your basic law of reflection. This is angle of incidence. This is angle of reflection. If your normal does not lie uh, is in such a way that this reflected ray is captured in a maximum way by the receiver, like there shouldn't be efficiency drop. The incident ray, whatever light energy you're getting from here, it should be reflected properly, and the receiver should be able to receive it. It shouldn't happen that this ray of light is falling and you are illuminating just this part of the receiver, then your efficiency drops, right? So we do not want that. So if a mirror is fixed, the problem would be sunlight would miss the receiver, and that is a major problem, and also efficiency drops drastically. Okay, so we must continuously rotate the mirror. It is very much required. Rotate the mirror is very important. Okay, so what does the mirror actually need to do? The mirror does not face the sun directly. It must satisfy just angle of incidence is equal to angle of reflection. It shouldn't be facing the sun. Only angle of incidence should be equal to angle of reflection. That means that the mirror normal must lie exactly halfway between which of them, the sun direction and the receiver direction. Okay, so you can have a very simple mental picture that if you want to bounce a ball from you to a wall, you should tilt your hand at half the angle, right? So that is a very basic idea that how the mirror should be mounted. Okay, so why can't we use simple azimuth elevation system? You might have seen that there are always comparisons between them. So in traditional systems, one motor is there for horizontal rotation and one for vertical tilt, right? So let's say you have a solar plate mounted over here. It can either be horizontally rotated, and it is also for vertical tilting, so that you can have your orientations in all the directions which can be facing the sun. But what are the problems with this? So I'll just write one motor for horizontal rotation and one motor for vertical tilt. Okay, so the problems associated with such systems are the following. What could be the problem? If you've gone to the lecture, I think you might know what are the drawbacks of using azimuth elevation system. What are the drawbacks? Anyone has any answer to this question? I mean, if you guys know, you can even list one of the drawbacks from your side. No one is answering, so I'll take you through it. But have you guys gone through the lecture? This was a simple lecture, I believe. Okay, let's move forward. So the problem is with this is large mirror is heavy, right? Because you just have one support on which you're supposed to mount the mirror. So large mirror is heavy. Okay, then wind pushes the mirror, which causes bending. Then it needs strong gearbox, and any gear backlash leads to positioning error. Okay, so what is the required accuracy that we want? It should be in order of 5 milliradians. So this is really small, this is extremely small. So the classical systems become heavy, expensive and less accurate. There comes the need for parallel manipulators. Okay. So what would happen? So which is stronger, one pillar or three pillars holding a roof? Definitely it is three pillars, right? One pillar is not wouldn't be able to take the load, or if it is able to take the load, three pillars would provide a more robust system. So three pillars, right? So parallel manipulators, what happens? Multiple legs support the mirror. Okay, the load is distributed. The bending is less and the stiffness is higher. I hope my voice is clear. If it is not clear, please let me know. You can always unmute
Clear, ma'am.
yourself or write something in the chat box.
Clear, ma'am.
Just a second, I'm not able to hear. Can you repeat?
Clear, ma'am.
Okay, thank you. So, for parallel manipulators, yeah, the stiffness would be higher if we have more number of legs and more number of supports. So, so these structures actually help us in carrying larger mirrors, less structural material is required, and it provides us better stiffness. So, this is the core mechanical advantage. Okay. So you might have seen in the lecture, the researchers at IISc Bangalore developed an RPS parallel manipulator. And what it is? It has a fixed base and it has a moving base. Okay. This is the moving base, which is a mirror. And this is the fixed base. Now what they have? They have RPS in between. Here is a rotary joint and then they have a prismatic joint and then there is a spherical joint. Okay. So similarly for these uh, legs also they have the same thing, RPS, and here also they have RPS, prismatic, and then this is RPS. Okay. So each leg, what does each leg have? each leg has a rotation at base, a sliding actuator which is meant by prismatic joint. Okay, and the third is a spherical joint which is basically like a ball at the top joint. So you can imagine, what can you imagine from here is three adjustable tripod legs holding a platform, and this is the platform. So if you extend one leg, any one of the legs, the platform tilts, right? So if we extend, I'll change the color. So if we extend this leg, let's say I rotate it in such a way that it goes like this, or this would be so. If I rotate it such that it goes like this, then there is a prismatic joint which adjusts the length, and then there is a spherical joint. So the new moving base would look like this, right? So if you extend one leg, platform tilts. If you extend all of them equally, then it is just that this platform goes up. So by changing the leg lengths, we control mirror orientation. All right. It is just simple as adjusting camera tripod. Okay. So this is an example of, it's very important, redundant manipulator. And why do we call it redundant? What do we need? We only need tilt in X and tilt in Y. That is it. We only need these things. But what do we have? We have three legs. Okay. So one actuator is extra. Right? And so you are aware, right, that this is only actuated at prismatic joint here, sorry, here and here. Okay, not at all the joints. So one actuator is extra. Okay, each actuator gives us flexibility in extra actuator gives us better stiffness. Better stiffness and flexibility in motion planning. Okay. So, but we must constrain one motion like height. That is why we usually fix the center height. Okay. Then the other manipulator that you might have already seen is UPU, which is hook joint, prismatic joint and hook joint. So now imagine instead of tripod legs, we design the joint so carefully so that the mirror rotates about a fixed center point. Okay. So if you see, so look at your wrist. Your wrist can rotate without translating much, right? So UPU behaves like a spherical wrist. That makes the orientation cleaner. Okay, we'll not go much into detail for this. But the main point that I had to discuss here is the mirror rotates about a fixed center point. Okay, so what happens? That makes the orientation cleaner. Okay, apart from that, you might have seen reconfigurable systems when you went through the lecture. So normally you would want either azimuth elevation system or target aligned system, right? You would need two different mechanical designs. But here, same hardware is used, different mathematical control is used, just change the rotation matrix. This is powerful. It means that software configuration instead of hardware redesign can be used. Okay. Okay. So, what do you think? Which would be better, RPS or UPU? You may think parallel manipulator is perfect. So, but the thing is, or rather, let's compare it to serial manipulators. So, parallel manipulators are very sensitive to manufacturing tolerance. They have a joint play and there are calibration errors. So, high stiffness alone is not enough. Precision manufacturing is very critical here. Okay. So this was very important. And apart from this, if we look at the very initial lectures, you might remember that when we started solar energy harvesting term, so we saw three major types of solar energy systems are there. What are they? They are flat photovoltaic panels. Okay. Then there are parabolic troughs. And then there is a disk concentrator. Okay. So for flat photovoltaic cells, the efficiency is around 18 to 20%. The storage is required, and are mainly basically they are installed as large installations like Kurnul 1 gigawatt plant. For parabolic trough, single axis tracking is done. Right, single axis tracking. And it focuses sunlight on a tube. Efficiency is about 20%. For disk concentrator, it is a parabolic dish. It has two axis motion. So it had one axis motion. Okay, it has two axis motion. It is focused onto Stirling engine and the efficiency is greater than, let's denote efficiency by eta. Efficiency is greater than 30%. So, concentrated solar power tower, right? CSP towers. It has, these CSP towers have 5,000 heliostats and they reflect sunlight to a receiver. Okay. The distance could be, so if you remember the image from the slides, they are placed at a, so there are 5,000 heliostats. All of them are placed in a curvature form, like many panels are there, and then all of them concentrate the light to a single receiver, and they can be at a distance of 500 to 1 kilometer as well. So from 1 kilometer this reflection is possible. The temperature of the receiver is very high, and then it gives a better thermodynamic efficiency, and the stored energy is stored as heat, and there are no batteries required. Okay. So in that, what is the thing? The sun moves, so we know already the sun moves 180 degrees in 12 hours, and it requires two axis motion definitely, and accuracy requirement is 5 milliradians. It is approximately equal to 0.29 degrees or 0.3 degrees. So extremely high pointing precision is required. Okay. But heliostat cost is 50% of the total investment. Okay. So it's much needed that we need to improve heliostat design, which is which actually gives a major economic impact. Okay. So existing heliostat configurations, I would just say there are two. Again, I would repeat, it is both of them azimuth elevation and target aligned. Okay, target aligned, you might know it is pinning elevation. So in both of them, there are two perpendicular rotation axes, and the mirror must align normally correctly. Laws of reflection should be satisfied. So mirror normal must bisect the incident ray and the reflected ray, and it should go to a receiver. Okay. Reflected ray in the direction of receiver, and this is direction of sun. So the limitations of existing heliostats are what? If you remember, wind loading causes deflection, requires heavy structural backing, and it also requires expensive speed reducers. So sun moves only at 15 degree per hour. It is very slow. We need very precise motion. All right. Then when we saw this RPS parallel manipulator, we saw all the whatever we get. It basically provides rotation about X and rotation about Y and translation about Z. Okay. So one actuator is redundant and it imposes a constraint that we have to keep ZC constant. Okay. So the kinematics of 3 RPS is something that we have already seen. So if we are given the sun position and the receiver position, we compute mirror normal using the reflection law and then orientation matrix. Then we apply the constraint equations. We get 8 equations in 8 unknowns. We use Bazou's elimination theory. We solve it numerically and compute the leg lengths. So this is a classical inverse kinematics problem with constraints. All right. Then if you had seen the simulation result, you have seen that it is simulated for Bangalore and the outputs were sun trajectory, mirror normal trajectory, etc. The leg length variation over the time, what is required. So we from there we could observe that leg lengths vary smoothly and it is a feasible actuator motion. Okay. Then after that for CAD they had used SolidWorks and they had also used this ANSYS software. Also, yeah, there were a couple of things. What was the wind speed and everything? I won't go into that. And then there was a experimental result. In UPU manipulator, universal and prismatic joint, you saw that the degree of freedom that they have is 3. There is special geometry, stationary center of rotation, spherical whisk behavior is there, etc. So there are 2 operating modes. There is azimuth elevation and target aligned mode. Rotation matrices derived from Euler angles. Switching possible without hardware change or they are reconfigurable systems. Okay. Then there is also spillage analysis. Image of mirror projection on receiver during 9 a.m. and 12 noon and 2 p.m. and 5 p.m. So spillage basically depends on configuration. Optimization is required. Okay. So from this first part of the lecture, we conclude that parallel manipulators for heliostats are there. We want more load capacity. We have more load. We can go with more load capacity. They have less structural weight. There are linear actuators possible, and they are reconfigurable. So accuracy improvement is needed, and it removes joint play, improves manufacturing tolerance. Okay. Okay. Then in the second part of the lecture, what do we have? We have Stewart platform. Stewart platform, what does it have? It has 6 adjustable legs. And it supports a platform. So parallel manipulator. Platform moves in 6 ways. What does it do? It moves forward. It moves sideways. It can move up. It can roll. It can pitch. It can yaw. So it is like a flight simulator base. So how it can become a sensor? Now if we lock all the motors, what would happen? The platform cannot move, right? Platform would not be able to move. If you push the top platform, the legs will experience forces. If you measure the torque, if you measure the force in each leg, you can compute the applied force and applied moment. That is what we want to compute. We want to compute applied force and we want to compute applied moment. So if you push the top platform after locking all the motors, when the platform is not able to move, if you apply the force, the legs would experience the forces. And if you measure the force in each leg, you can compute the applied force and applied moment. So this is like reverse thinking. Instead of using actuators to create the motion, we measure forces created by the external load. Okay. So here you might have seen there are many matrices that have come into picture. For example, H matrix is there. It connects the external force to leg force. Okay. So you can think of it like leveraging geometry. If the legs are vertical, they sense the vertical force very well. Okay. But bad at sensing the horizontal force. If legs are angled, then they sense horizontal forces better. Okay, so geometry defines the sensitivity. That geometry is captured by this matrix H. Okay, then let's talk about singularity. What does singularity mean conceptually? So system loses the stiffness in some direction. For example, if all the legs become parallel, the platform can move freely sideways, but it is bad for motion control, right? But for sensing near singularity, small external forces produces large internal leg forces that gives amplification. So singularity is bad for motion, but it is good for sensing. All right, so it is very important insight. Apart from that, so we already saw this. Okay, Stewart platform as sensors. We already saw that degree of freedom is 0 if the actuators are blocked, etc. Okay. The key equation that we have for Stewart platform is F is equal to H inverse F and M. Okay. And what does this mean? This means that this is the leg axial forces. Okay. F and M, both of them are combinedly external force moment, and this H depends on geometry. Okay, so if H is isotropic, what would happen? There would be equal sensitivity. Okay, if H is singular, there would be amplification in certain directions. So we can use singularity to enhance sensitivity. Okay, so singular configuration or singular directions are determined via the eigenvalues of H. If eigenvalue is equal to 0, it is a singular direction. If it is near singular, it means that there is a mechanical amplification and it is used intentionally for sensing small forces. All right. And then after this, I think the things were simple. It was a prototype development which was which was developed by ISRO, and it had flexible hinges and force sensing ring. And there was another prototype which had improved moment sensitivity. So I won't go into detail, but there were experimental results. Okay, so the basic thing is Stewart platform can act as motion platform, and it is 6-axis force torque sensor. Singularities can be exploited beneficially. Okay. Then in the next part, there was vibration isolation. Okay. So spacecraft suffers from reaction wheels. Let's talk about this. Okay. So spacecrafts suffer from reaction wheels, thrusters, okay, pump vibrations, and deployment shocks. So the requirement that we have is we want multi-axis isolation. Okay. So what we need? We need decoupled modes. Okay. Sorry. And we need narrow frequency band. And we need dynamic isotropy. So after this we can model, and for model you might have seen the equation of motion. Okay, before that, all of these, if you understood clearly, that these create the vibrations, and optical instruments are very sensitive. Even small microgravity vibrations matter. Okay, so we need isolations in X, Y, Z and roll pitch here. That is what we are talking here. Okay, and in all the 6 directions, and Stewart platform naturally has 6 legs, so it can isolate in all the 6 directions. What does this dynamic isotropy mean before we move forward? So suppose system has natural frequency in X. Let's say system has natural frequency in X as 10 Hz. Okay, natural frequency in Y as 40 Hz. Okay, so vibration isolation is uneven. Okay, we want all natural frequencies to be equal. Okay, then system behaves equal in all the directions, same in all the directions. So we define K as omega max upon omega min. If K is equal to 1, then it is perfect isotropy. And what they did, they achieved K to be equal to nearly 1.6, approximately 1.6, which is very good. Okay. Okay. After that, what is left? Okay. So for modeling, we saw the equation of motion, and it was mx double dot in simple robotics equation plus kx is equal to f, and this is eigenvalue problem you might have seen in the lecture. We want k minus omega square is equal to 0, and then the parameters here are RA, RB, alpha, beta and H. Okay, so I'm not going to detail. The thing was that we want to minimize K, which is omega max upon omega min. The goal is that all natural frequencies should be equal and dynamic isotropy index should be around 1.6, 1.7. Okay, so then there was experimental validation with the prototype, which was built with flexural joint and circular plate springs, and then there was a test. Okay, so yeah, all of these things were there. So the final conclusion is Stewart platform is a versatile system. It is a motion platform, it has number of sensors, and it also has a vibration isolator. So parallel robots are not only manipulators, they are precision engineering tools. All right. Okay. So so here I have not done all the maths, but I think If you've already gone through the lecture, it would be easy for you, because do you want me to go through the math that was covered? I covered it more on a conceptual side, but if you want me to write the derivations, I can write that. And that should be clear. So I'll just go through some of the things. So I think you might have seen this. The very first n is equal to s plus r upon mod of s plus r, right? Norm of s plus r. So what was it? Sun vector was s, receiver vector was r, and mirror normal was n. And then we wanted to find out what should be the direction of normal. Okay, and that direction of normal actually helps us decide how the angle should be, how the mirror should be mounted. So it gives us basic mirror orientation. Okay, then there was sun position in local frame. For that we had x pointing east, y usually north, and z was a zenith angle, and then etc. I'm not going into those details. Then for RPS manipulator, we know that degree of freedom is 3, and since we have more actuators and we want more number of motions, so we have to we have redundant actuation, and then we want to impose that c is a constant. Okay, so yeah, I think I'm scrolling through the slides and there are a number of equations, and I think you have already understood them. I won't go into those details. Okay, I will start with the questions now. Just hold on. Okay, so let's start with the first question. The concentrated solar power tower system for harvesting solar energy has the advantage over a photovoltaic system due to its higher efficiency. Then it can supply electricity at all times using batteries for storage. Okay, then it does not require accurate tracking of the sun and it uses a device called a heliostat. Okay, so the concentrated solar power tower system for harvesting solar energy has the advantage over a photovoltaic system due to its higher efficiency. It can supply electricity at all times using batteries for storage and does not require accurate tracking of the sun, which is definitely false, right? This, without any thought, you can put that this is false. We always require. Okay, so let's go with the first option. It has the advantage over a photovoltaic cell due to its higher efficiency. This is correct, because in a CSP, this is CSP tower. In a CSP tower, thousands of mirrors focus sunlight onto a receiver, right? Which, because of which very high temperatures are achieved, and high temperature means better thermodynamic efficiency. Okay, using the Brayton cycle. So efficiency comparison, if we compare for PV cells or for PV panels, what it is? It is 18 to 20%. And for dish concentrator or CSP tower, it is approximately 30%. So conceptually, if we talk, PV directly converts light to electricity, but CSP converts, so I think I should write this is important. PV, so if we compare the efficiency, it is 18 to 20% here, and for CSP towers, it is 30% or more. Okay. Then, conceptually, what does PV do? PV converts light directly to electricity. Okay. Whereas, what does CSP do? CSP converts light to heat, then to mechanical, and then to electricity. Because CSP operates at high temperature, it can achieve high Carnot efficiency. So this statement is conceptually correct. Okay. Then in the option B, we have it can store electricity, it can supply electricity at all times using batteries for storage. CSP towers typically store energy as thermal energy. Okay. It stores energy as thermal energy and not batteries. So they use molten salt storage or thermal storage tanks. Okay. This is the first reason. The second thing is the advantage of CSP is that it does not depend on batteries like PV does. Okay. So this PV requires batteries for night supply. They need electrical batteries for night supply. CSP stores the heat. It produces electricity even after sunset. So the statement is completely misleading and this is incorrect for both these reasons. Okay. The first reason being that it stores energy as thermal energy, and secondly that it depends on batteries. Okay. So it suggests that battery storage is the reason, which is correct. Okay. Then in option C, we have it does not require accurate tracking of the sun. This is completely false. CSP tower requires 5,000 plus heliostats. Okay. And it focuses sunlight on a receiver which is 500 meter to 1 kilometers away. So pointing accuracy we need there is approximately equal to 5 milliradians. So even a small angular error means that a reflected beam misses the receiver. So accurate tracking is absolutely critical. In fact, tracking accuracy requirement is much stricter than PV panels. So this option is conceptually correct. Okay? So sorry, incorrect. And let's talk about this. Did I miss something? I think okay, this is fourth and yeah, this is and then okay. In the fourth option, what do we have? It uses a device called heliostat. This we already saw that the heliostat is a mirror that tracks the sun. In CSP tower, there are thousands of heliostats. Each rotates in two axes, reflects sunlight to a central receiver, right? So without heliostats, CSP tower cannot function. So this statement is directly true. Okay. So just for quick memory trick, CSP tower does have heat, heliostat and high accuracy. For PV, it is just panel, battery and lower efficiency. Okay. So hence, these two are the correct options. Okay. I hope this is clear. Let's move to the second question. Sorry? I'm not able to hear you. Just a second. Okay, is it fine? Can you repeat your question? Akanksha, you were saying something. Can you please repeat your question? It's okay if you write in the chat box, that also works for me. Okay, I just saw the chat. Shravan said that something static like sound is coming from your side. I think that was the fan. I've turned it off if that works. Okay, I hope if you have any question, feel free to ask me. Okay, because I have this tab screen open on my screen. Sometimes I miss any chat is coming over or I do not get the updates. So in that case, please feel free to unmute yourself and ask me the question. Okay. Okay, we'll move to the second question. So the azimuth elevation configuration to track the sun requires two actuators in series requires two actuators in parallel okay, requires more than two actuators and it requires the mirror normal to be always pointed at the receiver. Okay, so the question says that this azimuth EL configuration, you might see it always, most of the times it is written as AZAL EL. Okay, so this configuration is used to track the sun, and then it requires how many actuators does it require in series, parallel, etc. This is the question. So let's go with option A. It requires two actuators in series. Okay, so how does azimuth elevation configuration works like? It has two axes of rotation, right? The first rotation, so let's talk about this thing first. So it has two rotations. The first rotation is about vertical axis. Okay, which is azimuth. And the second rotation is about horizontal axis, which is elevation. So physically this means one motor rotates the base horizontally, and on the top of that rotating base another motor tilts the mirror, right? So I already drew this figure, right? So one motor rotates the base horizontally so that it can move in either of the directions, and the other motor is used to tilt this base. So the second actuator is mounted on the on the output of the first actuator. On top of that rotating base, another motor tilts the motor. This is the whole point. So that means that motion 1 affects the frame of motion 2. Okay. So this is exactly what we call actuators connected in series, like a serial manipulator. For example, in human arm, the shoulder rotates and then the elbow rotates on top of the shoulder motion. This is series configuration. It is not parallel configuration. So azimuth elevation is the tool of serial mechanism. So option 1 is correct. Okay. The second option is it requires two actuators in parallel. Parallel means both actuators support the platform simultaneously, or both influence the motion at the same time, like Stewart platform legs that we saw. But in azimuth elevation, the first motor rotates the base and the second motor rotates the mirror relative to the rotated base, right? As in this case. So they are stacked and they do not jointly support the mirror. So this is not a parallel mechanism, right? So option B is incorrect for sure. Let's go with option C. It requires more than two actuators. So sun tracking requires 2 degrees of freedom, horizontal angle and vertical angle. So only 2 actuators are required. Adding more actuators would make it redundant, like RPS case which we saw, right? But the classical azimuth elevation design uses exactly 2 actuators. Therefore, option C is wrong. And why option D is correct or not correct? Let's see. Requires the mirror normal to be always pointed at the receiver. Okay. So the mirror normal does not point directly to the sun or receiver. It must lie halfway between the sun direction and the receiver direction. So the reflection law means angle of incidence is equal to angle of reflection, right? So the mirror normal bisects the angle between sun vector and the receiver vector. So if the normal pointed directly at the receiver, the reflection would be wrong. It would go somewhere else. And that is not what we want. We would be missing all the receiving rays. So option D misunderstands the physics of reflection and hence this is incorrect. So we have the correct option to be only the first one. Okay. So as always keep in mind, azimuth elevation is like camera tripod head. The base rotates, then the tilt happens on top of it. Okay. So there are 2 actuators, serial connection and series configuration. All right. Okay. Let's move to the next question. This is not an MCQ, it is something that you have to solve. The pointing accuracy required in milliradians for a mirror size of 1 meter cross 1 meter located at a distance of 500 meter from the receiver of size 2 meter cross 2 meter in a concentrated solar power CSP tower system for harvesting solar energy is okay. That is the answer that we want to find out. What is the pointing accuracy required for a mirror size of 1 meter cross 1 meter? It is located at a distance of 500 meter from the receiver of size 2 meter cross 2 meter in a CSP tower system for harvesting solar energy. What should be the pointing accuracy? What would be the pointing accuracy? So it is a very good question, and let's answer this question. And we already know that we get it to be equal to 2 milliradians per second, and we want it to be ideally in the same way. But let's solve it. So what is given to you? You're given that the mirror size is 1 meter cross 1 meter and the receiver size is 2 meter cross 2 meter. So the distance from, just a second, the distance from mirror to receiver is 500 meters. Okay. So we must find the allowable angular error. So what does pointing error mean? First thing. What does this mean? If the mirror is misaligned by a small angle theta, if the mirror is misaligned by a small angle, and this theta is in the order of around milliradians, okay, small angle theta, the reflected beam shifts at the receiver. You cannot shift the receiver. Okay, so if the mirror is misaligned by just a small angle theta, the reflected beam shifts at the receiver, and it would also be by theta. So by small angle approximation, if you assume it to be a circle and then if you take the small angle, you will see that the linear shift happens by approximately L into theta, where your L is 500 meters and then your theta is angular error in radians. Okay, so what is the allowable linear shift that we have? Let's talk about that. Okay, so your mirror size is 1 meter. Okay, and your receiver size is 2 meter. Let's talk about just one side of the mirror. So receiver is larger than mirror projection to ensure that a reflected beam still lands inside the receiver. Okay, so the maximum allowable shift that we have is half the extra margin. So what it is? Receiver width minus mirror width. It would be 2 minus 1 meter. So what is the allowable shift on one side? It would be 1 upon 2, which is 0.5 meters. Okay, so this is the maximum permissible displacement. Okay, so let's convert this linear shift to angular error. So what would be theta? It would be shift upon L. Okay, the permissible shift that I have is 0.5 upon L is 500. So from here your theta is approximately 0.001 radian, which is approximately 1 milliradian. Okay, but there is a very important point. Mirror rotation error doubles reflected beam deviation, because if the mirror is rotated by theta, okay, what would happen? Reflected ray changes by 2 theta. This is simple geometry. Okay, if you rotate the mirror by theta, the reflected ray would shift by 2 theta, not just by theta. So your 2 theta is equal to 0.5 upon 500. From here you get it to be equal, theta to be equal to 0.0005 radian. Okay, okay, so but practical derivation which is used in heliostat system accounts for total image spread geometry and realistic tolerances. When calculated carefully using beam geometry and worst case condition, required pointing accuracy comes close to 2 milliradian. Okay, so from here uh, we can, I guess we do not need to go for this, but we can go with this answer of 1 milliradian. Okay, this is actually not required. But so the case is 5 milliradian sometime was a general system requirement, but either distance is 500 meter, receiver is only 2 meter by 2 meter, so allowable angular error must be tighter. 500 millirad would cause 2.5 meter shift, and that exceeds the receiver size, and we cannot go with this. So it is not, I think it is zero point 0.5 milliradian per second, zero point 0.5 milliradian, but we can go with this answer directly, okay? So 2 milliradian is reasonable engineering compromise, okay? And we should go by it. So the small angle relationship that we use, shift is equal to L theta, that was important. And reflection doubles angular error. Longer distance means tighter accuracy. Smaller receiver means tighter accuracy. Hence, it's 2 milliradians approximately. Okay. Which question it is? Third. Okay. The main advantage or advantages, it can be multiple answer. In sun tracking, using the 3-DOF UPU parallel manipulator, is R that it is a redundant system and hence easier to control. Okay. That the extra joint results in less pointing error in sun tracking. Then it can be switched electronically. To achieve less losses in focusing the sun's energy onto the receiver. I'll explain the question, just hold on for some time. Receiver, and then that is easier to manufacture. Okay, so let's see. The main advantages in sun tracking using the 3 UPU parallel manipulators are that it is redundant system and hence easier to control. Is it like that? Or that the extra joint results in less pointing error in sun tracking. It can be switched electronically to achieve less losses in focusing the sun's energy to the receiver, and that it is easier to manufacture. So let's go through the options one by one. Okay, so what is the advantage that we have? So uh, let's see the C option first, because I would like to go with it because it would give you much what is happening over here. So 3 UPU manipulator is electronically reconfigurable. What does that mean? It can operate in azimuth angle, elevation mode, and then it can also work in target aligned mode without changing the hardware. Only the control law or the rotation matrix changes. And why this is important? Because different configurations produce different spillage losses. Right, energy missing the receiver, that is defined by the spillage losses. So by switching control strategy electronically, we can choose the configuration that gives minimum image distortion, that reduces the energy loss, that improves the efficiency. Okay, so the key advantage is same mechanical structure is used but different software configuration is used and it also leads to reduction in optical loss. That is why this option is correct. Now let's talk about the first option. It is a redundant system and hence easier to control. Redundancy does not automatically mean it is easier control. In fact, redundancy usually makes control more complex because there are, in many cases, there are infinite possible solutions, okay? And then there could be need of optimization to select one. So 3-degree UPU is not primarily advantageous because it is redundant. Its key advantage is reconfigurability and not ease of control. So option A is conceptually incorrect. Let's talk about option B. The extra joints result in less pointing error in sun tracking. Okay. So extra joints do not automatically reduce the pointing error. Okay. This is completely wrong. And why? Pointing error depends on manufacturing tolerance. Okay. It depends on joint play. We already discussed all of this. It also depends on calibration and depends on structural stiffness. So more joints may even increase error if the tolerances accumulate. So simply adding a joint does not guarantee better accuracy. Okay. Therefore, option B is incorrect. Okay, let's move to option D. It is easier to manufacture. Parallel manipulators are usually more complex, require precise alignment and require careful joint fabrication. So they are definitely not easier to manufacture than simple azimuth elevation systems. So it is definitely incorrect. Okay. So what you can understand from here is that the main advantage of 3-degree UPU manipulator is not redundancy, not extra joints and not manufacturing ease, but it is software based switching, reduced spillage losses and electronic reconfiguration. Okay. And why do we have reduced spillage losses? Just because of the facility that we have for electronic reconfiguration. All right. Okay. Okay, this is a question directly from your notes. So in the statics of a Stewart platform, the external forces and moments F and M acting on the top platform are related to the vector of leg forces F as, just for hint, here you will have the notations. J and H are the two Jacobians. Okay. Sorry, J and H are, this is Jacobian and this is force transformation matrix. Okay. So the options here are F is J transpose F M transpose. Okay. Then the second option is J inverse transpose F and M, forces and moments ka transpose. The third option is H transpose F and M ka transpose, and the fourth option is F is H inverse F and M ka transpose. So I think I do not need to go through it, and the option must be very clear to you. What is the correct one? It's H inverse Fm transpose, right? This is directly from the lecture. And so the thing is, what is happening physically? You understand this, right? That W is F and M forces and moments. They are written as one matrix. So the top platform experiences an external wrench, which is given by this, and then each leg experiences an axial force Fi, and the six leg forces together must balance the external wrench. So what happens physically? Physically, your external wrench is basically sum of contributions of leg forces. So what you will get from here, you can find the forces and moments transpose as H into F, where H depends purely on geometry, right? Leg directions and moment arms, etc. And F is the vector of six leg axial forces. Okay. After this, what do? You solve for the leg forces. Whatever you get, you multiply both the sides by H inverse, है ना? And then you get the option which is correct. So that is why this is correct. H transforms the leg forces to platform wrench. So to go reverse, we need to go from wrench to the leg forces. So geometry matrix inverted gives us the required leg forces. This is physically logical. Okay. The first option that we had consisted of Jacobian. This confuses Jacobian with force transformation matrix. Don't ever go for this option. J relates the velocities, H relates the forces. Alright, we won't go with Jacobian because it relates the velocities. We would go with H because it relates the forces. It is force transformation matrix. In general, H can be written as J transpose. Okay, the relation between the forces comes in terms of J transpose. But here the question clearly defines J as Jacobian and H as the force transformation matrix. So using J transpose directly is incorrect in this context. Okay. For the second option, we have J inverse transpose. We already have, so this is mathematically unnecessary, I believe, because inversion must be of H and not J transpose inverse. So conceptually, you invert the force mapping matrix and not the velocity Jacobian. That is why we have not written it. Why would you do that if you have H in the option? Okay. In the third option, we see that taking transpose does not inverse the transformation. Transpose changes rows to columns only and it does not reverse the mapping. Force equilibrium requires solving linear equations, not transposing them. So transpose is conceptually wrong here. So you have to remember a few things. I'm listing them down here. X dot is related to Q dot by Jacobian and the force relationship is torque is equal to J transpose. Alright. In Stewart statics, W is H into F and F is H inverse W. That's all. Always invert the mapping matrix. Okay. So I think we are done with the correct answer. Okay. Let's move to the next question. Which of the following is or can be are true for the force transformation matrix H in a 6 degree of freedom Gauss-Stewart platform? Okay. So from here the first option is H is not a proper matrix as the elements in its column do not have the same units. Okay. H is same for all configurations of 6 of GH platforms the rank of H can never be less than 6 and the determinant of H can be 0 for certain leg arrangements. It's just talking about this force transformation matrix, and let's go through the options one by one. Okay, so for stand, what H represents? Okay, so we already saw Fm transpose is represented by H into F, where F is leg axial forces. Okay, F and M are external wrench. Okay, H depends purely on geometry. Okay, so what is the structure of S? The top three rows, I'm not writing it completely, but the top three rows are direction cosines which are dimensionless, and the bottom three rows are moment arms which are length units, which have length units. Okay, so statement 1 is H is not a proper matrix as the elements in its column do not have the same units. If you look carefully, each column of A contains top part which is unit vector components and they are dimensionless. Okay. If you want me to write, I'll write. Just hold on for a second. And the bottom part, what does that contain? It contains R cross U mainly, which has units of length. Okay. So one column contains unitless numbers and the other column contains length units which are in meters. That means columns do not have uniform units. In strict mathematical sense, this is not dimensionally homogeneous. That is why statement 1 is true. Okay. So H mixes forces and moment effects. That's the reason. The second thing is H is same for all configurations of 6 for Gauss Stewart. Why am I writing H? GS platforms. This is absolutely false. Why? Because H depends on leg directions, platform orientation, and joint positions. Leg directions, platform orientation, and joint positions. Okay, so if the platform moves, if this platform moves, the leg directions change, the moment arms change, and therefore the H changes. Leg directions would change, moment arms would change, and therefore the H changes. So H is configuration dependent, hence this is also incorrect. Okay. For the third statement, the rank of H can never be less than 6. If H loses rank, determinant of H would be equal to 0. This means singularity. Stewart platform absolutely can become singular for certain leg geometries. At singularity, the rank drops. Certain forces cannot be resisted. So, rank can be less than 6. Right? So, this is also incorrect. And the fourth option is determinant of H can be 0 for certain leg arrangements. When does this happen? When the legs, so what could be the cases for this? If the legs become coplanar, okay, or legs intersect at a point, or certain symmetric arrangements are there. At all those configurations, the determinant of H would be equal to 0. That means the platform is singular. It loses stiffness in some direction. So the statement 4 is true. Any confusion in this question? So the conceptual summary that we have here is, think of H as geometry matrix that converts leg forces to wrench. So units are mixed. It is not dimensionally homogeneous. It depends on configuration. It can become singular and rank can drop. So H is not a proper matrix because the units differ, and determinant of H can be equal to 0. Make sense? Let's go with the next question. In the Gauss-Stewart platform, base sensors presented in the lecture, what it is? The Gauss-Stewart platform is an isotropic configuration. It is a singular configuration. These things remain the same. In third, it is the GS platform cannot measure some component of externally applied moment. Okay. The GS platform cannot measure some components of externally applied forces. Okay. So what is true about it? So let's start. So first, what was special about the sensor design? In motion platform, when we want motion, we usually say, oh, we have achieved singularity and that is a problem. Singularity is bad. It causes loss of stiffness. The platform becomes uncontrollable. But in the sensor application, something different was done, right? The platform was placed in a near singular configuration intentionally, right? And why? Because near singularity, small external wrench gives us large internal leg forces. This is the case when singularity is approaching. Near singular configuration, what happens? Small external wrench gives us large internal leg forces. This gives mechanical amplification. This term is very important. Mechanical amplification. This increases the sensitivity, so singularity becomes useful for sensing. Okay. So the first option that we have here is, okay, before that, let's talk about the second option first, singular configuration. In statics, we know that Fm is equal to H into F, where F is the actual leg forces. The determinant of H is equal to 0 near the singularity. That means, and it causes the losing of rank that we saw in the last question. So from here, H inverse becomes very large, and even small applied force produces large measurable leg forces that improves the resolution. Therefore, the sensor was intentionally designed near singularity. Hence, the correct option is it works in a singular configuration. Okay. The option 1 is the platform is an isotropic configuration. What does isotropic mean? It means that equal sensitivity in all the directions. Okay, but in the sensor we want enhanced sensitivity in certain directions. For example, moment about z-axis. That does not mean isotropic behavior. That means anisotropic behavior. So it is not isotropic. So that is why this is incorrect. The third option is the platform cannot measure some component of externally applied moment. Okay. If it were exactly singular, yes, some directions would be completely unmeasurable. But in practice, it is near singular, not completely singular. So all components can still be measured, just sensitivity varies. So this statement is false. For the fourth option again, I have the same reason. Same reasoning is there. It is near singular, sensitivity is changing, but measurement is still possible. Complete inability only happens at exact singularity. Sensor operates near singularity, not at full singularity. So this is incorrect. Okay. So in general, whenever you need read robotics, this is something you will come across. Singularity is bad for motion control, but for sensing, singularity can be exploited for force amplification. This is very powerful. Okay. So the Gauss-Stewart platform is in a singular configuration. That is why the second option is the correct one. All right. I hope this is clear. Let's move to the next question. Consider a Gauss-Stewart platform with the connection points given by B1 P1, B2 P2, B3 P3, B4 P4, similarly till B6 P6. Okay, with all legs parallel. Okay, and along the vertical direction. An external force of 1 Newton is applied in the vertical direction. Okay. So what happens? The leg forces are all equal and each is 1 Newton, are all equal and each is 1 by 6 Newton, cannot be obtained. And the last option is are infinite. Okay, I think this is very simple question and you should be able to answer. Okay, so this is 6 Gauss-Stewart platform. The connections are given to you B1, P1, B2, P2, etc. All the legs are parallel, all the legs are vertical, and the external force 1 Newton is being applied vertically. So what are the leg forces? Okay, so just understand the geometry first. All the legs are parallel, vertical, and they have the identical arrangement. This means that there is complete symmetry, there are no horizontal components, and there are no moments generated. So each leg can only each leg can carry only a vertical force, right? So if Fz in our case is equal to 1 Newton, so all of the forces F1 plus F2 plus F3 plus F4 plus F5 plus F6 should be equal to 1 Newton. Each leg must carry equal share, right? This is very simple. So the total Fi should be equal to F, 6F should be equal to 1 and F should be equal to 1 by 6 Newton. Alright, so the correct option is B. Why the correct option is B? Because all the legs are identical or are vertical, the load is symmetric, and there is no reason for unequal distribution. So the forces divide equally among all of them. This is simple statics. The first option was each leg, each is 1 Newton. Okay, so if each leg carried 1 Newton, total support force would be 6 Newton, but the applied load is only 1 Newton, so this violates the equilibrium, so it is incorrect. The other option is it cannot be obtained. Nothing indeterminate is here, right? System is very symmetric. It is statically determinate in variation in vertical direction, and the leg forces can be computed easily. Then the other option is are infinite. Infinite forces occur when the system is singular. Forces are applied in uncontrollable direction. Here force is along the leg direction, so system can easily resist it. So forces are finite and are small. So the configuration is singular for horizontal forces, moments, but not singular for vertical force. All right. You cannot say that it is never singular. It is singular for, I'll write this down. This configuration is singular for horizontal forces and moments. Okay, but it is not singular for vertical forces. So singularity depends on force direction. It is a very important concept. All right. So this is also incorrect, this is also incorrect. So each leg carries 1 by 6 Newton. All right. Okay, after this let's move to the next question. The vector along a leg I in a Gauss-Stewart platform is given by if B naught and P naught denote the base and platform coordinate system, then PI, T and BI are what? Are defined how? That is basically the question. I write the options. Are all defined in B naught. Okay. Are all defined in P naught. PI and T are defined in B naught and T is defined in P naught. D is PI is defined in P naught and T and BI are defined in B naught. So what is the correct option? This is again a conceptual question. So vector along the leg I is, hold on, vector along the leg I is given by this. Okay, this represents position of a platform PI expressed in base frame B naught minus the base point BI. Let's decode each term carefully. What is PI here? PI is location of the attachment point on the top platform. Okay. Since it is attached to the moving platform, it is naturally defined as the platform frame P naught. So Pi is defined in P naught. Now what is R? R is the rotation matrix frame. Rotation matrix. And it is a rotation matrix from what? From platform frame to base frame. Okay. So it is written in this way, from P naught to B naught. So it transforms platform coordinate frame to base coordinates. Okay. What is T? T is the translation vector from origin of base frame to origin of platform frame. Okay. So it must be expressed in base frame B naught. Why? Because we added to a vector already, already transformed into base frame. So vectors can only be added if expressed in the same frame, right? So T is also defined in B naught. What is BI? BI is the base attachment point that is fixed in base. So naturally BI is defined as in B naught. Putting it all together, what we get is RPI plus T minus BI, right? PI, take PI in platform frame, okay? Platform frame, rotate it into the base frame by using the rotation matrix, add translation T to it and subtract the base point BI, which is also in the base frame. So PI is in platform frame, it is multiplied by a rotation matrix so that we get it in base frame. T is also in base frame, BI is also in base frame. So the other options which we have here are, all of them are defined in B naught. No, if Pi were already in B naught, we would not need rotation matrix R, which is used over here. So this is wrong. All are defined in P naught. No, this is also wrong. If everything were defined in the platform frame, then subtracting Bi would not make sense because Bi belongs to the base. So it is incorrect. Okay. The third option is Pi and T are defined in B naught and T is defined in P naught. This is internally inconsistent. Translation vector, which is T here, must be expressed in the same frame as final computation. So it is wrong. Okay. So this is also incorrect and the last option is correct because Pi is defined in platform frame and TIBI both are defined in base frame. So in rigid body kinematics, global position is rotation matrix into some local position plus translation is also defined in the base frame. Where local position is defined in the moving frame, R converts it, T is defined in the global frame, etc. So the correct option is this one. Alright. I hope there is no confusion with this. If not, then let's move to the next question. Okay. For the sixth component, the Stewart platform sensors, which was presented in the lecture, singular configurations were chosen since they are easier to manufacture, they are very sensitive to, for all components of externally applied forces and moments, the desired mechanical amplification in chosen direction are possible, and they can measure all components of externally applied forces and moments with equal sensitivity. Okay, so the question is for six, just hold on, for the six components GS platform sensors, since singular configurations were chosen, since they are easier to manufacture, they are very sensitive for all components of external applied forces and moments, they are desired mechanical amplification is chosen in chosen directions are possible, and then they can measure all components of externally applied forces and moments with equal sensitivity. Okay, so first five, would anyone choose a singular configuration? Singularity is bad normally in robotics, right? It leads to a lot of, I have been repeating this over and over again so that you get a hold of this. So there is loss of stiffness, there is loss of control, and there are infinite velocities, right? But in force sensing, something different happens. If you recall the statics equation, it is this, right? So H inverse that we get here is very large. That means small external force causes large leg forces. That is mechanical amplification that increases the sensitivity of strain gauges. So singularity becomes useful. So the correct option is desired mechanical amplification in chosen directions are possible. Okay. Near singularity, one eigenvalue of H becomes small. Corresponding direction gets amplified. That direction becomes highly sensitive. Designers can choose which force moment direction to amplify. For examples, amplify MZ, okay, if torque sensing is important. So singularity gives directional amplification and tunable sensitivity. That is exactly what we want. Okay, the other option is, so the first option here is they are easy to manufacture. Singular geometry does not make fabrication easier. Okay, manufacturing complexity has nothing to do with singularity. In fact, singular configurations may require precise alignment. So this is false. Okay, very sensitive to all components is the second question, is the second option. So near singularity, sensitivity is high only in certain directions. Other directions may have normal or even reduced sensitivity. So amplification is directional and not uniform. Thus this is incorrect. Okay, the okay, so the last option is they can measure all components of externally applied forces and moments with equal sensitivity. Equal sensitivity means isotropic configuration. Singular configuration is the opposite of isotropic. In isotropic case, your condition number is 1. In singular case, the condition number is infinity. So equal sensitivity is not achieved, hence it is wrong. So the big conceptual insight that we have here is singularity is bad for motion control, but it is good for force amplification. In the sensor, they intentionally choose near singular configuration to amplify specific force moment components. That is smart engineering. Okay, so the correct option is desired mechanical amplification in chosen directions are possible. All right, I hope this is clear. We will go with one more question and then we'll end the class. Okay, so hopefully all of these questions will be very helpful for you. So the last question that we are carrying over here is for the 6 component Gauss Stewart platform, sensors presented, which are presented in the lecture, of course. Ring shaped force sensing elements were used since. Why were they used is the question. It is easiest to fix strain gauges on them. Okay. At the midsection, the strains are maximum for a given leg force. The deflection is least due to the force acting in the legs. Okay, and they can be easily accommodated in the sensor. Okay, so this is the question. For a 6-component Gauss-Stewart platform, sensors which are presented in the lecture, the ring-shaped force sensing elements were used since it is easiest to fix strain gauges on them. At the midsection, the strains are maximum for a given leg force. The deflection is least due to force acting on the legs, and they can be easily accommodated in the sensor. Okay, so what is the purpose of the ring element is the first question that we should ask, and then we'll be able to decide on the options. So you know very well that in the Stewart platform sensor, each leg carries axial force, and that force must be measured accurately. Strain gauges are mounted on a deformable element. So the ring shaped element, okay, acts as flexural element. Okay, it deforms when the axial force passes through it. So we want, what do we want? We want maximum measurable strain, and we also want maximum measurable strain for a given applied force, whatever force is applied, because strain gauge output is directly proportional to strain. More strain, better sensitivity, better resolution. So the correct answer here is at the midsection, the strains are maximum for a given leg force. Think of a circular ring under load. When axial force passes through the ring, the bending occurs, right? Maximum bending stress happens at specific midsections of the ring. Just like if there is a beam which is under bending, the maximum stress occurs at the outer fibers. Similarly, in a ring element, the midsection experiences maximum bending strain. Okay, that is exactly where strain gauges are placed. So the ring geometry is chosen to concentrate strain, increase sensitivity, and improve signal to noise ratio. Hence this is correct. Okay. The first option was easiest to fix strain gauges. Ease of attaching strain gauges is not the main design criteria. Any flat surface can allow strain gauge attachment. Okay. So the ring was chosen for mechanical amplification and it is not for convenience. So this is incorrect. The other option is deflection is least. For sensing, we do not want minimum deflection. We want measurable deformation. If it is too stiff, small strain is there and poor sensitivity is there. So least deflection is opposite of what is desired. So this is also incorrect. And the last option is it can be easily accommodated in a sensor. Primary goal, so mechanical compactness is secondary, but the primary goal is maximum strain per unit force. So this option misses the real reason. So this is also incorrect. All right. I have couple of more questions, which I think if I go on writing, I won't be able to complete it. But I think I would. Okay, I would go with one more question, but I won't write it. I would just speak. For example, if you're since you are in the class, so you'll be able to hear and then decide on the answers. And if it is a recording, you'll definitely be able to see. You'll be able to listen. So for the 6 component same Gauss-Stewart platform, all the questions are related to that. Flexural joints are used since kinematic joints have friction, which results in inaccurate measurements. The desired bending stiffness can be obtained. They can withstand more loading, or they are easier to model and analyze. Okay, so what is the goal of the sensor? External force in the in the Stewart platform, force torque sensor, external force is actually measured by the leg axial force is transformed to it, and the leg axial force gives us the strain, and strain is the electrical signal. We want pure force transmission, we want no energy loss, we want no hysteresis and no nonlinear effect. So the correct option is kinematic joints have friction, which results in inaccurate measurement, which was the first option. And the reason is normal joints have friction, they have backlash, they have the static friction, and they have hysteresis. What happens if friction exists? External forces are applied, some force would be lost in joint friction, not fully transmitted to sensing element. So measured force won't be equal to the actual force. This causes inaccuracy and poor repeatability. So flexural joints are used. There are no sliding surfaces, no friction, no backlash, and it is a pure elastic deformation. So they provide smooth force transmission, better accuracy, etc. So that is why these flexural joints are used. So desired bending stiffness can be obtained is wrong, because flexural joints do affect stiffness, but that is not the primary reason here. The main issue is the friction elimination. They can withstand more loading. Flexural joints usually withstand less load than rigid mechanical joints, hence this is wrong. They are chosen for precision and not strength. The other option is easier to model and analyze. Flexural joints may even be more complex to model because it is beam theory, it is compliance. Ease of modeling is not the reason. Hence, that option is also incorrect. Okay. Just another question I'm taking. This is the last question. So a traditional 6 Gauss-Stewart platform cannot be singular in all 6 directions at the same time, can be statically isotropic, cannot have dynamic isotropy, or can be dynamically isotropic. Okay. So the first statement is it cannot be singular in all 6 directions at the same time. This is correct. Why? Because determinant of H matrix is equal to 0. That implies rank of H is less than 6. Okay. So when singular, system loses stiffness in at least one direction, but not necessarily in all the directions. If it was singular in all 6 directions, rank would be 0. No force could be transmitted, legs would be contributing nothing. So that would mean platform is completely disconnected mechanically. Physically impossible, because even if legs are arranged badly, they will resist force in at least one direction along their axis. Okay. So complete 6 direction singularity cannot happen. Hence this statement is true. The other option is it can be statically isotropic. Okay. Static isotropy means equal force sensitivity in all the 6 directions. Condition number of H would be equal to 1. So, special geometries can achieve static isotropy. So, a traditional 6-6 platform can be statically isotropic. Therefore, the statement is not selected as universally true or false in this context. Okay. The other option is it cannot have dynamic isotropy. Dynamic isotropy means all natural frequencies are equal. So, for a traditional 6-6 Stewart platform, mass distribution is not symmetric enough. Inertia coupling exists, right? And stiffness matrix is not perfectly isotropic dynamically. So, natural frequencies do differ. That means dynamic isotropy cannot be achieved in traditional configuration. That is why we saw in the lecture as well, in probably the last part, that optimization was required to approach dynamic isotropy. So this statement is true. And the last option is it can be dynamically isotropic. I think the last option was, yeah, it can be dynamically isotropic. So traditional 6-6 GS problem does not automatically give equal eigenvalues. It requires special optimization and geometry changes, so it cannot be dynamically isotropic by default. Hence, it is wrong. Okay. So the summary that we have in this question is that Singularity can lose stiffness in some directions, cannot lose stiffness in all the 6 directions at the same time. Also, dynamic isotropy is very difficult and it requires optimized geometry, not natural property of standard 6.6 GS platform. So the final answers that we have here is that it cannot be singular in all the same directions at the same time. Also, it cannot have a dynamic isotropy. All right. Okay. So this was the last question that we took here. And in the next week, we are going to deal with velocity and static analysis of manipulators, where we'll see series manipulator Jacobian matrix. So we'll be doing this Jacobian work very formally there. Parallel manipulators Jacobian matrix, and singularities in serial and parallel manipulators, statics of serials and serial and parallel manipulators. Okay. So this is all that we'll be covering in the next week. Please watch all the lectures before you come to this tutorial session. It would be really helpful for you. If you do not watch, you will miss out on many of the concepts. Even if I try to cover everything, it is not possible to cover in this short amount of time with all the questions that we have to take up for your practice purposes. So please go through the lecture, watch the lecture, and then come to the class. It would be very helpful for you. Okay. So next class we'll be seeing this velocity and static analysis of manipulators, and then okay, so we'll meet next Monday at the same time, 6 to 8 p.m. Thank you. Bye bye.